Okay, so there's been a great deal of hype over the last couple of years about the Internet of Things. And despite that, or more probably because of it, there's a lot of confusion about what the Internet of Things actually is and what it means going forward. Right now, our computing is diffusing out into our environment. The desktop is increasingly becoming intended for niche users. It isn't dead, but like the mainframe, it's going to slowly fade behind the scenes, backstage. Developers and designers, people like you and me, will need it. We will continue to need it. But despite the prevalent view in Silicon Valley, the world is not made of people like us. Most people are perfectly happy with the desktop going away. They never liked computers in the first place. So for the rest of the world then? Well, everyday objects are already becoming smarter. And in 10 years' time, every piece of clothing you wear, everything you carry with you, will be measuring, calculating, and weighing your life. In 10 years' time, the world is going to be full of sensors and the distributed computing that powers them. Right now, these sensors live in our cell phones, all of which come laden with accelerometers and gyroscopes and magnetometers. Some even have thermometers and pressure and humidity sensors. But today's mobile devices, the cell phones, are transition technology, artifacts of a stage of technological progress. Like the beige box that sat under our desk for 20 years, these too shall pass and fade into its own niche. Because what you really need to remember is this is not a phone. This is just a computer that happens to be able to make phone calls. So it's not just our cell phones anymore, it's our things. Things like internet-enabled light bulbs, weather stations, electricity monitors, smart thermostats, or even cars. The Tesla Model S, for instance, is just a web server with a wheel in each corner and a really big UPS in the middle. So there is a problem. The commercial IoT as we know it today, and if you're in Corey's talk this morning, his keynote, you might have heard about some of those problems. The commercial IoT has a lot of problems. And because of that, because what a lot of people can't seem to understand, the Internet of Things done right, isn't just taking an existing thing and putting an internet connection in the thing. About 2 years ago now, I think it was Samsung introduced a smart washing machine. Others have followed. This is Whirlpool's version, released at last year's CES in Las Vegas. It boasts Wi-Fi and a colored control screen. It can be started from an iPhone app and will text you or email you when your clothes are done. It costs $1,700 US, as does the smart dryer that goes with it. And if you're wondering who would want to buy one of these things, you're not alone. Even Whirlpool's not entirely sure. They've been quoted as saying, "We're a little bit of a hammer looking for a nail right now." And this is about their own product, something they are trying to sell us. That's because they haven't got the point. They have a thing, and they've connected it to the internet. And despite the name, that's not what the Internet of Things is about. The Internet of Things isn't anything to do with connecting things to the internet. And no, I really think the acronym isn't the best thing in the world, but we're stuck with it now. This is not a smart washing machine. A smart washing machine would have a single button to turn it on and off. When you turned it on, it would look at the NFC tags in all of the clothes you've put in it and figure out what to do by itself. And then when it was nearly done, it would tell your heating system to turn your radiators on so that you could dry your washing on your radiators. You have radiators in this country, right? Yeah, you know what I'm talking about. You dry your washing on your radiators so you wouldn't have to buy the smart dryer to go with the smart washing machine. Only then would it send you a push notification to tell you to come and unload it, because we haven't quite got robotics down to that sort of level yet. Now, that would be smart. So despite the fact that having a lot of commercial IoT things in my home, that's what happens if you run an IoT startup every once in a while, and like a lot of people right now, the working pieces of smart technology in my home are things I've built or modified or hacked on myself. Because the real problem with the Internet of Things is that all of the things have to talk to one another, or it's not a network. And if we're the things that connect the things, that's really missing the point. And commercial IoT isn't really very good at that right now. Now, most of the Internet of Things I've built make use of this thing, an Arduino, or a Raspberry Pi. But until very recently, they didn't come with wireless networking on board, and it's not exactly a cheap way to build things, especially when you want lots of things, which is where the ESP8266 comes in, which Brian Jepson, who used to work at Make and now works at O'Reilly, said, "This is inexpensive enough to be very much in the territory of thousands of sensors launched out of a cannon, cheap," which is a really quite decent quote. So this is the ESP8266, and I wish it had a better name, but it doesn't, so we're stuck with that too. Originally, it was released as a serial to Wi-Fi bridge. The default firmware uses an AT command set to allow you to configure and use it. In other words, it could provide Wi-Fi access to other microcontrollers like the Arduino. But it cost $2. $2. It was so cheap, people started to look into the proprietary Chinese written documentation to try and figure out, what on earth could this thing do? And what they figured out was it's actually an 80 megahertz microcontroller with full Wi-Fi support, both as client and access point. It does 802.11bgn. It supports WPA and WPA2. It's got a full TCP stack. It's got DNS support. It's got GPIO. It's got I2C. It's got I2S, SPI, PWM support, and a 10-bit ADC. This is actually a fairly awesome piece of kit. Did I mention it was $2? Actually, it's less than $2. If you buy in reasonable quantities, it can be had for something like $1.25. And modules bearing this chip are all over the place, made by various manufacturers. This is the ESP01. It was the first one to appear, and is still probably the most commonly available. You can pick this up for $2 on AliExpress. Perfect for this, I actually logged into AliExpress and checked the price. In fact, the cheapest I could find it for was $1.64 per piece, with free shipping via China Post. It takes 90 days to get to you, but there's still free shipping. I bought 100. I'm not sure what I'm going to do with them when I get them, but in 90 days I'll probably figure it out. The ESP01 is fairly bare bones. You only have very limited access to the GPIO in the chip, and there's a bunch of, but there are a bunch of other breakout form factors, a confusingly large number, in fact. This is the ESP12 module, which has been integrated onto a carrier board. It's the Adafruit Huzzah. This does not cost $1.64. It costs $9.95, which is still pretty cheap. And it's a lot easier to work with than the ESP01, which is something we'll find out in a few moments when we start actually playing with hardware. Effectively, computing has become cheap enough that we can throw it away. We can build sensors, and for $1.64, I'm happy to throw them away at the end. This is no longer we're treasuring our single Arduino board that we have in the house and we switch between projects. We just build the projects, seal it inside silicon glue or something, and throw it away, or keep using it. There are 9 usable GPIO pins. Normally, pins 6 through 11 are connected to the flash memory in most cases. Some modules break out more than others. For instance, the insanely cheap ESP01 only really gives you access to GPIO 0 and GPIO 2. Since GPIO 0 is the thing that toggles it into boot mode, you can't really use GPIO 0 particularly well, so you really only have one GPIO pin, which is sort of meh. But hey, did I mention $1.64? Anyway, it also, the 01 also has some pins tied to high or low, so you have to be quite careful about what code you put on it. If it's the wrong code, you can actually brick the module, and it's not very good. Anyway, other modules like the Adafruit Huzzah, which I showed you in the last slide, give you access to all the pins. As well as being cheap, it doesn't, at least for a Y-side chipset, use all that much power. These are current draws using 3.3 volt power, a temperature of about 25 Celsius, based around a 90% duty cycle. These are probably the lines you want to be most concerned about. It's quoting there about 140 milliamps. I actually normally see about 85 milliamps in most operational circumstances. But the thing you really should note there is the deep sleep mode, 10 milliamps. Most of that power draw is actually from the LED the power LED. And you can just cut the trace to that, and then it drops to pretty much nothing. And in case you're a bit afraid of putting things to sleep, if you have bad experiences with putting microcontrollers to sleep in the past, this is also designed to wake from deep sleep and to transmit packets in less than 2 milliseconds, which is actually pretty cool. That means with conservative use of sleep mode and a reasonable duty cycle, you can continuously run the module using just solar power all day, all night. This is, I mean, that might not sound a huge achievement, but this is a 200 milliamp hour LiPo and a 0.5 watt solar panel, and that will suffice to run this particular breakout board, which is the SparkFun Thing. I'm sure they had lots of fun coming up with that name, more or less continuously. The availability of good sleep support in a microcontroller is pretty much vital for if you're going to build distributed Internet of Things, and the ESP8266 has that. So what can you actually do with it? Well, this is a Wi-Fi hat for the Raspberry Pi Zero. Has anyone actually managed to get a Raspberry Pi Zero? Like, wow. Yeah, they're hard to get, aren't they? This actually makes use of the SDIO support on the Pi, because yes, the 8266 has SDIO support. So basically, this for $4 or $5, you can build Wi-Fi for the Pi Zero that doesn't actually block your USB ports, which is actually pretty cool. So if you actually need heavy-duty CPU, you can use this and the Pi Zero, and you've got all the power of the Pi out in the field. Despite not actually using this, the full power of the chip, this is actually in the original AT command set mode, where it's just used as a serial to Wi-Fi bridge. This uses an Esperino and a light-sensitive diode to measure electricity usage. So basically, you get the little flashing light in your electricity meter when you do a click. This is actually just watching for those clicks and measuring your electricity usage, which is pretty cool. Whoop, what happened there? OK. This is an internet-connected world clock with 256 full-color LEDs, which spell out the current time, weather conditions, and weather forecasts in words and numbers. Weather data is downloaded from the Weather Underground every 15 minutes, and the display is comprised of 256 addressable WS8212 node pixel LEDs in 8 rows of 32. It's all run from an ESP8266. There's also a little remote notification near the door. They'll tell you if it's raining outside, if you can't look out the window. A lot of IoT right now is the why don't we just look out the window stage. I'm sure that will get better. This is a DI weather station. It houses a DHT22 and a BMP280. Basically, it's a battery-powered NetAtmo clone, if you've come across the NetAtmo. It can pretty much operate for about a week, 4 measurements an hour. And measurements are sent via MQTT to a Raspberry Pi housed somewhere else in the house. And that's actually a fairly common pattern we're starting to see with this. A number of disposably cheap 8266 chips scattered around in the field, streaming data back to a Raspberry Pi safely hidden in someone's closet. Amongst other things, that takes the sensors off your home network and keeps them on a separate, nice Wi-Fi network that you don't have to worry about, so it adds a little bit more security. There's also some insane things that can be done with the chip, and most of them being done by Charles Lohr. This is the Ethernet. It's an ESP8266 I2S-based software 10-base-T Ethernet solution. It does its own Manchester encoding, decoding, framing, FCS, and only uses 2 pins on the chip. It was announced on April the 1st, but the joke was it really wasn't a joke. I bow down to this man. It's an massively impressive thing to have done, and is totally useless for all possible actual practical purposes. This is another one of his projects. It's an ESP8266 analog broadcast television interface. Hook an antenna a length of wire, in other words, up to the GPIO 3RX. Tune your analog NTSC TV to channel 3, power on the ESP, and this is what happens. For $2, you can turn your old analog TVs into remote consoles. Bear in mind, this is not entirely legal. Just like the Raspberry Pi FM radio hack, where you pretty much did attach a piece of wire to a Raspberry Pi, it's not legal. On the other hand, it's got a range of about 100 foot, so even if you have a ham radio enthusiast living next door, you're probably okay. It's not exactly the Internet of Things, but I had to show it because it's insanely cool and shows up how much grunt the CPU actually had. That's a 3D render done in real time on the chip while it serves a web interface to tell you the next thing it's going to broadcast via its Wi-Fi. That's how much grunt you actually have to play with. So let's get hands-on with this thing. And this is where this talk will now go absolutely AWOL, because I'm about to try and do live coding on Wi-Fi hardware at OSCON. Yay me. OK, so this is the footprint of the ESP01. And while it's physically compatible with the breadboard, it's not electrically compatible. In other words, you plug this into the breadboard, it short circuits itself, and the magic smoke comes out, which is not good. Don't let the magic smoke out. So this is what we actually have to do. We connect it up to a FTDI connector to the laptop, and then we have to pull GPIO low for firmware upload, and then push GPIO to high for firmware upload. And then once the firmware is on the board, we disconnect it, unplug those wires, replug it in. So what I'm going to do to start off with is, once we've got it all wired up, it's actually really easy to use the community tools. Remember, most of the work done in this is done by the community. It wasn't done by the manufacturer. It's really easy to use the community tools to upload firmware. And the first firmware we're going to look at is the really simple AT command firmware that came with the board to start with, that you will probably never, ever use. But it's quite cool. So it's a good start. So let's have a look at that. OK. So if we mirror our display, how's that? People see that? OK, so what I'm going to do is I'm going to plug this in here. And over here, nope. 2. Come on. Yay, over here. So I've got to bear in mind, that's going to take a long time to switch. Over here, we've got one of these ESP01 modules, and a whole bunch of wires, which I wasn't going to actually bother doing live on stage, because hey, I'm sure you've seen people plug wires in before. So what we'll just do is we will connect the RX to TX, the TX to RX. Don't get them the wrong way around, or you'll get very confused why things aren't working. A ground pin and a power pin, and with a bit of luck, yes, the light should go on. Can you see that? Yes, we can see that. OK. So Oop. OK, so what we've got here is we've got esptool.py. It's a Python program that's been built to ship firmware up onto the board. It's writing via the serial port the binary firmware onto the board. So with a bit of luck, it'll actually do that. So I'm going to warn you that at some point during this presentation, I will almost certainly have to reboot my laptop. Because one of the things is, while the community tools are great, they are evolving very quickly, which means they're not exactly all that stable. Which means every so often they tend to lock up the serial ports. And as anyone using OS X serial can tell you, the only way to get rid of that is to reboot the laptop, restart the kernel, and everything goes away. There's 4 different failure modes, which I guess I'll talk about if we ever get to one of the failure modes. So yeah, don't be too surprised if I suddenly start pulling my hair out and reboot the laptop. That's a good time for questions. Very good time for questions. So what this is doing is just pushing the firmware up, raising it into the flash on the chip. With a bit of luck, we should get a success message very soon. Leaving, that's good. Right, so then what I want to do is I want to detach the power here. Then I want to pull the wires, because this is one of the ways you can brick the serial ports. So this is pulling the GPIO wires apart so that it doesn't no longer in boot mode, and we will boot it up. And we get a red light, and at that point we can talk to the thing. So just rescan serial ports. Yeah, I still have one. So we're 115, 200 BPS. If we connect, we should get a bunch of junk. Is that big enough font for everyone? Yep, good. We had an error, so if I hit AT, I should get an OK back. Hurrah! So this is basically in its fundamental mode. It's the mode where it is just serial to Wi-Fi. And what we're going to do is I'm going to put it into client mode. And then I'm going to reset it. We should get a bunch of junk in a second. There we go. It's ready to go. And then I'm going to look for a Wi-Fi network. And this is where we find out there's no Wi-Fi in this room. No, yay, we have Wi-Fi. So these are all the Wi-Fi APs it can see. You can see there's a lot of Oscon Wi-Fi. So what we're then going to do is AP join the access point. We're going to join Oscon. Presumably, it just picks whichever one it's the highest strength. And it doesn't have a password. So we're good. And with a bit of luck, we should have an IP address. So this is, it's doing the DNS dance. Yay, we have an IP address. So it's managed to make it onto the network. The next stage, I know, I'm so happy. So the next stage is, anyone that does live coding demos knows exactly how stressful this is. So we're just going to put it into asynchronous modes. So we're going to basically attach a thread to, on the chip to this request. And then we are going to start a thread to grab the Google homepage. OK, and we're linked. So that means it's made it out into the world, and it's now connected to a server somewhere in the depths of Google. So now what we want to do is we're going to send some characters to Google, and we want to get the homepage, please, and we want HTTP 1.1. And I give this a 50% chance of success. Yeah, I didn't think this was going to work. OK. So effectively, what it's doing, you can see that you have to play with it. It's like there's a lot of commands that have to go back and forth. It's not the best thing in the world. This is not how you really want to do Wi-Fi, because you're going to have to program all of these commands into your microcontroller. You're going to have to send all these text strings up to the serial port on your Arduino or your Raspberry Pi or whatever, and then you're going to have to do this negotiation. What happens when this would finally return, which it probably is not going to do. Let's be honest here. It's not going to return anything. But what it would finally do is you would get return packets. So basically, you would get chunks of HTML back. And then you have to reassemble the web pages back from these chunks of HTML, exactly how the browser actually does it, which is not a great, fun thing to do on a microcontroller with limited availability. So I'm just going to give up on this. I didn't think it was going to work, not really. And we will look at something else in a bit. So I'm going to pull this out, take that away, and close that because we won't need it again. Actually, let's keep that open. Right. So while it's pretty useful, and I've seen lots of people use it for interesting things, I really use the AT firmware myself, because these days the firmware there's a firmware for pretty much every language under the sun. The first one to come along was Lua firmware. It's probably the most used right now. But Lua, Python, Lisp, JavaScript, And it's even got full-blown Arduino support now, which is what I mostly use it in. There's also a basic firmware for anyone that were the hankering for the 1980s. So as I said, probably amongst the first community firmware was Node MCU. It's a Lua-based firmware. And the same people have an ESP12 module. You can see the thing, that's the SMD module on top of the carrier board there. Based board, which is also called Node MCU, which is not confusing in the slightest, obviously. This is actually a really good breakout. I prefer the Adafruit Huzzah for various reasons. But nonetheless. Anyway, so I'm an Arduino guy from way back. So right now I'm mostly using these boards as the cheapest Arduinos on the planet, effectively. And Arduino Sport started out fairly complicated to get around. It was like an entire custom build of the IDE you had to install. But now with 1.6, it's purely a module you just install from the boards manager. That's it. You download the Arduino IDE, you pull up the boards manager, you search for ESP8266, you hit go, you're done. That's all you have to do. Which is really pretty cool. Arduino people in the audience? Yeah, so if you can use it in Arduino, you can use one of these. So I was pondering what I was going to do for the real demo as opposed to the little tiny demo. And I was going to, what I was going to do for the talk. And then this happened. This is the Amend and Dash button for the Internet of Things. It sounds great in theory, and seemingly quite affordable at 20 bucks, until you realize that the battery is not rechargeable and only lasts 1,000 pushes. That's 2 cents a push for anyone that can't do basic math. There's no counter to tell you how many clicks you have left. And the heartbreaking thing, the thing that will tear at every single open source person's heart in this room, is that it's a AAA battery soldered to the circuit board. Yay! So today we're going to build our own. And my button's going to light up, because obviously, it has to have more features than the closed source competitor. This is the Adafruit Huzzah. And this is pretty much all you have to do to wire a button up to this thing and make it light up. Effectively, you've got one pin to register the buttons, and you've got one pin to light the LED. You'll see 2 resistors there. One is a pull-down resistor for the button, and the other is a resistor in line for the LED. If you're here for the last talk, you saw the presenter just plugging the LED into the pins of the Arduino. Yeah, don't do that. Because basically you stand the chance of putting too much current through the LED and it goes pop. Most LEDs you can get away with it. The Arduino doesn't push too much current through its pins. This LED on this particular button I'm using, which is from SparkFun, which is really nice. It's a really nice, cool button if you need something to light up. That really doesn't cope with excess current very well and blows up at the slightest provocation. So yeah, it needs resistors. At the other end of things, if I can make this one contact the internet, it's slightly more. This demo is slightly more reliable. Google doesn't like random things coming from conference networks, and sometimes I should have picked a different page. Never mind. Anyway, to make things simple, I'm going to hook it into IFTTT, which is not open source, but hey, we can use any web endpoint we want, and I want to use this one, which makes it fine because I want to do it. You can use any HTTP website point you like, which means you run your Raspberry Pi, and you can push things via HTTP back to your Raspberry Pi. The end result can look like this, or at least can be made to. This is the whole thing, which is a battery, a LiPo management board, the Adafruit Huzzah, the button, the resistors, can all be fit into a 9-volt battery box, which is repurposed with a hole drill for the button. Cool thing about that is you can actually use the on-off switch that went with the battery to turn the connection between the battery and your board on and off so that you can save some extra power. The one we're going to build today isn't going to look like that. It's going to look like this because, hey, it's a little black box, and that's far too. And I didn't bring any drills with me, so that's a thing. So let's get started. The first thing we just take a brief look at the hardware. and 2. And here we go. So let's just go a bit zoom in. And as you can see, it's pretty much exactly what I had up on the screen. You've got an Adafruit Huzzah. I was using pins 12 and 14 to connect to the button. You've got your resistors. And then you've got this, which is the thing that, whoops, that's my hands, not any wires. You've got these wires which come out and talk back to the laptop. As you can see from that, which is the production version, you don't need to connect to the laptop. We're just going to get some serial output, and so that we actually know it's working, or in the very likely case, so we know it's not working and why, and therefore I can say, at least claim it was doing something. Yeah, I don't know why I decided to demo Wi-Fi hardware at OSCON, but there we go. It was a good idea at the time. So let's mirror our displays and jump back into the Arduino stuff. So, okay, so this is some stub code I wrote because, oops, this is not stub code. That's still a picture of hardware. Okay, this is some stub code I wrote because seeing someone write code to bounce a button up and down isn't really that interesting. You can see what I do here is I just start serial connection. I've got a couple of pins here, one for the button, one for the light that lights up. Then what we do here is we connect to the Wi-Fi. So it has its own ESP8266 Wi-Fi library, which operates very much like the Arduino's own. So Wi-Fi begin, we wait for it to actually connect to the Wi-Fi. When we're connected, we grab an IP address, we grab an RSSI, and we print that up down to the serial port. Simple as that. You can see here, one of the things that trips up a lot of people is, oh no, it's not, hey, we did that, okay, that's fine. So then in the loop, what I do is I just read the current state of the button. I also, as well as doing the debouncing via the resistor, I'm doing a software debouncing. So basically, we just loop through here, look at the button state, look at the last button state, see if it's changed recently. For those that don't know, what you actually get in buttons, you get a lot of flicker. So you want to make sure that when people press it down, you're going to see a constant value from the button rather than like just a little bit of flicker on the thing. So this is getting rid of noise. So effectively, it means that you're not accidentally triggering the button push every 5 seconds. Let's do a little bit of code then. So what we also need is, no, go away. We're going to connect it to IFTTT. And for anyone worried, really, yeah, okay. So if we go to this, I'm just going to show you the recipe. No, go away. So basically, this makes use of the IFTT's maker channel. If you haven't come across that, effectively, it's something you can send a random HTTP request to IFTTT, and they will do something with it. So it's if they get a random HTTP request, we do something with it. In this case, I'm actually going to send a notification to my phone. So if it receives the web request called button pressed, it will send a push notification to my iPhone that says, hey, event name button pressed occurred on the maker channel. You can do a whole bunch of other things. You can turn on lights. You can play your thing, play music, whatever. Doesn't matter. For anyone worried about my API key here, this is not actually my main account and will be deleted after this presentation, so that's not a problem. OK, so we've got this. So what we need to do is we need to define which host we want to connect to. So we just grab const.car host equals maker.ifttt.com, and then we have const.car star key equals this long string of random letters here. There we go. And so we go in here. And what we're going to do is we're going to grab a Wi-Fi client. And then we want a string, which is the URL, which is trigger button pressed with key. And then we just URL plus equals the key itself, URL plus equals question mark value. You can pass 3 values back, and one of the things I'm doing is I'm going to pass the number of times we've pushed the button for no particular reason, just so to show how to do it. So then if we client.connect to our host on port 80, then we're going to serial.println. We're going to print out. I'm going to do a lot of serial prints here, just so when it doesn't work, you'll at least see where it didn't work. So that's http:// serial.println host. Everyone okay with the font size? Yeah. Okay. So if client.connect host 80 serial.print wow, I've write passive Raspberry Pi too many times. I automatically, instead of starting requesting, I started writing Raspberry Pi. Requesting URL. And so then we go to our client, and we're going to println get, so string get http plus host plus URL plus string http 1.1. If anyone sees typos, please tell me. Don't put it after I laugh when it doesn't work. Quotes and quotes. Thank you. I've made that one several times. I don't know why. Okay, so then we have a client.println string host. I mean, you can see exactly what I'm doing here, right? Which is we're building an HTTP request by hand. And obviously, normally you'd wrap this away in some library. But here we're just going to do it by hand. And then we're going to just delay for a second or so. And then else serial.println didn't work. And then we're going to return from that. So then what we need to do is while clients available string line equals clients read string until we're looking for end of line here, and we're going to print out the response, and then serial.println, and we're done. Okay, so hopefully this compiles. Wow, okay. And what I'll do is I'll just hook up this. And we got a couple of minutes, yeah? You're going to say no, aren't you? Okay, we're almost there. All right, so what I need to do is unpull that. I'm going to put this in bootloader mode, which involves holding down this little button. And we get a red light on that. And then hopefully what we do is we upload it. Yes, it's uploading. OK, so effectively what's going to happen is that it'll see the button push. I hit the button. It'll make an HTTP request off to IFTTT. And with a bit of luck, my phone will then get a push notification. We'll see. If not, we'll look at the serial terminal, and we'll see a whole bunch of things going wrong. And we'll see how that works. OK, so what now I have to do is I can just open the serial monitor. I can hit reset. OK. It got a thing. And if we push this, OK. And it did actually go. So we'll just do that again here, where you can see it. You can see that the button pressed event went, but if I push here, light goes on, things happen, and there's the button push event. And that is how it should work. And there we go. So if you're interested in learning more things, with a bit of luck, this should come up. There we go. And here are some URLs that you might want. So get your phones out, take the pictures. Pretty much this has all of the information that you need to do stuff with this. I'm actually writing a book about this stuff for O'Reilly right now, but it's late. It's not going to actually make it. It was supposed to make it for OSCON, but it didn't. But you can find out what you need there. Thank you.